Let's start lecture 24. So today, actually we covered LPMLN and we have a few slides left there, but mostly the content is there. So we covered the LPMLN language in 2 class days, and today what we are going to do is to actually connect the recent formalisms that you learned. So actually let's first finish up what we were doing for the LPMLN system. So this is one use of LPMLN system. If you have a base net, it can be easily encoded in the language of LPMLN, and you can use the system LPMLN to ASP, which we will actually talk about underlying principle this class. Basically, this system translates LPMLN language into the answer set programming language, so that you can use Klingo to compute the LPMLN language. Now, from the user's perspective, they don't need to know what is underlying language. It's possible that users don't know about Klingo language, but he can actually view this as just LPMLN. So the first part is we define the probability distribution. So given the table, probability distribution table, we can encode this as a fact. So if you have like 0.02 is the probability of tempering is true, then we can write this line to say the tempering is true with 0.02 chance. Okay, and we talk about this, why this particular encoding works. Log of p over 1 minus p. When it is chosen, then the probability, the weight it will receive is e to the power of p over 1 minus p. So in general, if you have log of p over 1 minus p of certain fact, okay, if this fact is true, then the probability will be e to the power of log of p 1 minus p, which is actually p over 1 minus p, versus if it is not chosen, then it's e to the power of 0. Okay, so the relative strength is this is actually same as p over 1 minus p versus 1. Now, if you normalize it, what happens is this is actually same as p over 1 minus p. Okay, so you can use this encoding to say that this fact is true with probability p. Okay, and we did that sometime before. If you are not sure about what I'm talking now, then you can go back to that slides where we introduced this way. Okay, all right. So each of the entries in the probability table can be represented by one line, as you see here. Okay. And the DAG part can be represented by this rule. Okay, so the parent comes into the body, and the child comes into the head. So tempering is true if this fact is true. Okay. In the more general case, you will see like this one, alarm becomes true when tempering is true and fire is true. But also, you have to check that the probability fact associated with this condition is true. Okay, and same for the all other combinations. So in basically one edge in here, which is actually these two edges can be represented by these 4 lines. Okay, so each of the edges give true or false. So when you combine it, it has 2 times 2 possibilities. So there are 4 rules that you can write. Okay, so otherwise encoding is actually pretty straightforward. And we talk about how to use this system to compute the probability. So probability of fire being true, given that alarm and tempering is true, we write into the database fact that the evidence part that alarm is true and tempering is also true. And then we call the system using the usual command line as we know in alchemy. Okay, actually this should be actually fire, which was actually shaded by the picture. Okay, So that's actually what we need to do. If you have negation of tempering, then all you need to change is from this positive fact into the negative fact. Okay? And so basically we have seen this kind of thing. What if we know that there's nothing, we know what is the probability of fire, and if we know, then we give the condition and ask for fire being true, and we can keep this. And depending on what you put into the condition, when you put query, you get different inference. So sometimes you have the cause, and you want to know the probability of the effect, or you can also go vice versa, or you can also reason about the other cause. So if if tempering is true, and also alarm is true, then what is the probability of fire? Okay, so those intercausal inference can be also done in the way that we described before. What we didn't say last time was the same domain can be represented by different implementation of LPMLN, which is called LPMLN to MLN. And as the name implies, we can also convert LPMLN language into the MLN so that you can use alchemy to compute. So underlying solver here is actually alchemy, or there are actually two other inference engines for MLN that this system actually uses. As you can see, the input language is somewhat close to alchemy, but also is somewhat close to ASP. So let's see. The beginning part is actually similar to alchemy. So we declare the domain, the sort and object, and these are the predicate declarations. So this part is exactly the same as alchemy. And actually these are also the same. In the input language of alchemy, we don't have this function log, so we have to actually compute this manually and then feed it here. Okay. In the rule part, you see that we are using this symbol to represent arrow, which is actually what in alchemy corresponds to this direction. Okay, but the language is actually versatile. You can either write in the backward or forward, doesn't matter. But this is the symbol for the arrow, and the other things are actually also, there's not much things to notice. I mean, there are a couple of conventions that for the ASCII notation, instead of comma, as in the previous language, or in ASP, in alchemy it uses this caret symbol, so we have to write conjunction in this way, but that's all. Okay, however, so the input language is actually very similar, but the computation is actually different. So let me actually show you how it operates. So, okay, so this is the program that you just saw. Okay, okay. So how do we call? So this is the command line. Let me just go here. Okay, so first we want to find out the probability of fire being true without knowing anything else. Okay, so I give the empty file. Other than that, this command line is the same. The output that you see is more, actually, as you guess, it is coming from the alchemy. So there is a long part here that you will probably not able to read, and we are going to actually talk about what all these things are about. What happens in the system is there is a certain conversion method from the LPMLN language into the input language of alchemy, and so these parts are something that the system adds automatically. Okay, and then it calls alchemy and doing the sampling, and as you see, the fire is actually here. Okay, so you can actually give different condition, and let me just try. This is not the same. Okay, so here in the database, we actually put the same database fact as in alchemy, so we don't have to write this colon dash as in the input language of ASP. Okay, so we can just write either positive fact or negative fact is just exclamation mark followed by the symbol. Okay, so I can actually write report and maybe not tempering. So as you just give as much information as you know. Okay, and if you call, yeah, the phi is actually 27%. It's actually more increased than before. Okay, so what we will do today is actually how this is done. So today will be the class that connects these different formalisms. So we have covered ASP and Markov logic and coming into the language of LPMLN. Okay, so I mean, having done this, actually, how are they related? So some direction may seem obvious. Maybe by now you know how this can be related to this. Okay, but let's try to make it more formal. Okay, so today we are going to see many different translations. It's in fact possible that you can understand ASP as a special case of LPMLN. That's no surprise. Markov logic as a special case of LPMLN. A bit more surprise, but not too much. What's more interesting is actually LPMLN can be converted back to ASP and as well as Markov logic. And then you may wonder, then what's all these things? Why do we have all these different formalisms? Well, ultimately, the program that you're running is converted into the machine code and binary code, and it will be run at that level. So it's actually whatever the high-level programming language that you use, it does not matter in terms of machine point of view. It's actually what human is the problem there, right? So what way that a human can program better. Same as in knowledge representation. So some languages are good at modeling this concept. Some are doing better for the others. You may get some, I don't know, maybe when you do the homework, you may have some idea that what works well in ASP actually doesn't work well in Markov logic. Okay, because the implementation that you work with doesn't have those choice and aggregate, which might have been useful if you're there, but that was not in the language of alchemy, and also vice versa. So if I taught alchemy before and then Klingo later, you will also encounter similar issue. I want to express certain uncertainty, but there is no natural way to do that in there. Okay, and LPMLN is also there, but who knows? This also has certain weakness it has to overcome. So, but in the end, it's actually interesting that people develop this kind of language. They focus on certain aspects, so try to make it more versatile and try to say certain aspect of knowledge can be encoded nicely into this in this language. But when they compute, that doesn't necessarily have to follow the original language, and that happens a lot in the history of knowledge representation. In fact, we covered set solvers DPLL algorithm before, and although the classical logic, the propositional logic is very simple, but set solvers are very powerful. So what happens is you can actually convert those languages like ASP or Markov logic, you can convert them into the input language of set solvers, and you compute certain things from there. So from the human point of view, propositional logic is too low level to work with. It's like an assembly language. But in the end, when you model this in terms of high level language, you can actually compile that into the low level language. And the low level implementation can actually work better. Okay, so rather than designing proprietary implementation of the high level language. Okay. And this is not only in the, of course, in the knowledge representation. If you work with any kind of computer science, there is a notion of reduction. So you can reduce problem A to problem B, so that you can use solver for B to solve problem A. So that's actually very often in the case. Right. So we are going to see some instances of that fact today. Okay. So the first direction from ASP to MLN. Okay, so what's your guess here? can we translate ASP into LPMLN?
Yes, everything infinite.
Everything is infinite? Then can we capture that? Okay, let's see whether that's actually true. I can give you some head up there. It's not necessarily true. So I'll ask you at some point, when does that break? Okay? But anyway, this first thing to note here is, so suppose you have answer set program pi. We can view this as a special case if you assign infinite weight to each of the rules. Okay? So let's look at this example first. This pi is ASP program, and we can translate or convert into pretty much similar rule in LPMLN, where the rule has infinite weight. Okay, good. That's good. Now, what the theorem says is this. Okay, so that gives the hint to the question that I'm going to ask. So for any answer set program pi, the deterministic stable model of pi, which means just a stable model of Klingo program that you saw before, are exactly the probabilistic stable models of LPMLN program, p pi, where p pi is obtained by this simple translation. Now, among the all these probabilistic stable models, you only look at the stable model whose weight is e to the power of k alpha, where k is the number of all ground rules. Okay, that seems to be too long statement, so let's actually look at the example. Okay, so how many interpretations are possible if you have p and q in the signature? 4. Okay, good. So let's actually play with this. By the way, we know what are the stable models of original program, right? We don't have to compute. What are the stable models?
Only P, only Q.
Okay. So there are 2 stable models, singleton set P and singleton set Q. Okay. There are 2 other interpretation, empty set and the total set PQ. They do not make a stable model. Okay. All right. So let's see. Now, what happens with each of these interpretation? Let's start with the empty set. Okay. So empty set. How do you find the weight of the interpretation empty set? Let's look at this one. Okay, this program. Okay. So first, we have to do what? Subset that is true under this interpretation. So what is that subset? So empty set means Q is false and P is false, right? So does that interpretation satisfy the first rule? No. Why? Because false and negation is true, so this is true implies false. So the first rule is not satisfied, second rule is also not satisfied by the same reason. Okay, so the subset is actually empty. Okay, good. So so after that, what do we check? If empty set is the stable model of the empty rule, is it?
Yes.
Yes or no? So for this one, pi subscript I, actually I should say p pi subscript I is actually empty. That's what we just checked, right? So what do? We have to check whether empty set is a stable model of the empty program. And it's obviously true, right? That's the minimal information that you can derive from the empty program. All right, so then what is the weight? So e to the power of the number of rules that are true, right? So we have to add up all those weight, but there's nothing to add. Then what is the identity? E to the power of 0. So we get e to the power 0. Are we together? Okay, maybe this is a two-corner case, but there's actually nothing special if you just follow the definition. Okay? Or do you want me to explain this again or not? No? Okay. So let's go to the next one. So what is the subset here? Subset of the program that is true under P.
The first rule.
The first rule is true.
And
So
second,
this is true.
yeah,
What about the second one?
this true.
Ah, okay. So this one says P is true and Q is false. Then this is actually true because P is true is in the head, so obviously this is true. And this is also true because not P is in the body, so that's obviously true. The whole implication is actually true. So the subset that we have to look at is the whole program, and is P a stable model of the subset? Yes. Then what is the weight?
E to the power 2 alpha.
E to the power of 2 alpha. Good. The second one is symmetric, so it should be e to the power of 2 alpha. Now the next one, PQ. Does it set? So what is the subset that is true under this PQ?
MPC.
Are you sure about that? Both of them. Right? Not Q implies P. This is true. This is true. The head is true. So no matter what the body is true or false, the rule is true. So the subset is also the whole program. Are we together? Okay. Is PQ a stable model of the whole program?
No.
Obviously not. So what is the weight?
0. It will be
0. Good. No, it's not e to the 0. It's actually 0. Okay, so there's a slight difference between the first case and the last case. All right, good. So, as you see, what the theorem says is when you do this translation, not all the progressive stable models correspond to the original stable models, right? So these two correspond to the original stable models, right? From the original program, but this is actually an additional thing which doesn't correspond to the stable model in the original program. Okay, so that's why this is actually important. The weight should be e to the power of k alpha, where k is the whole rules. In other words, you have to use all rules in the original program. Okay, are we together? Good. All right, so another thing is this. If pi has at least, actually, I should actually skip these things. Okay, this is actually incorrect, so let me actually skip this discussion. But anyway, so from ASP to MLN, we know that we can use the actually no, something is okay, let me actually add something here, which is actually a bit tricky. Now if you look at the weight, of course this guy does not correspond to the original program. What I didn't actually say yet is actually the probability of pi. Okay? Alright, so what is the probability in this case? Probability has to be normalized, right? So what is the probability of this guy?
0.
It's actually limit alpha going to infinity, okay, e to the power of 0, divided by the whole weight, which is e to the power of 0 plus 2 times e to the power of 2 alpha, right? And what is this value? 0. So this actually probability gets 0. Okay. Same way, of course, this is obviously 0. What about this guy?
Half.
This guy gives half and half. So although the weight is actually not 0, weight is not 0, but the probability can be 0 because of these hard rules. Okay. So this additional sentence is saying it's not about the weight. That was about the statement here, but about the probability. You can actually look at the probability of the interpretation. Okay. In fact, when we translate ASP into LPMLN, all the stable models with non-zero probability will have the same probability. Okay, so P and Q has both non-zero probability, and they are equal. Okay, so each of them is actually the stable models of the original program. Okay, are we together? Good. So the last statement was actually assuming this condition: if pi has at least one deterministic stable model. So in the previous example, the original program has actually two stable models, right? Deterministic stable models. So this condition could apply. However, the condition is actually critical. If you miss this condition, the next sentence is actually not true. Okay? Can you find out the reason? Okay, what I just said was in the previous example. Okay, compute all the probability. So if you see, let's think about this way. So suppose you have very weird case. You don't have ASP solver, but you have LPMLN solver. Okay, now you want to compute ASP using LPMLN solver. How can you do that? You translate ASP into LPMLN and then call LPMLN solver, and it returns some stable models that has non-zero probability, and they happen to be equal. Okay, they should be equal. So you can actually extract the stable models of the original program by looking at these. So the stable models that has non-zero probability is P and Q. So P and Q must be the stable models of the original program. So that's how you can solve ASP using the implementation of LPMLN solver. Okay? But what I'm saying is, that's not necessarily true if this condition is missing. In the previous example, the pi that you started with has at least one stable model. It's called consistent. Okay? So there is at least one stable model. But if the original program doesn't have stable models, then something goes wrong. Something goes wrong here.
So if so probabilistic stable models can be more than the number of stable models. So if nothing can achieve e to the power k alpha, then after normalization some might get non-zero probability.
Okay, that's fine. But what does it have to do with the original program? Okay, let's actually look at this example. Okay, so original program. What is the stable model of original program? This one. If you call Klingo, what will happen? It's unsatisfiable, no stable model. So this is actually, there's none. What about stable models here? Do you recall? How many stable models were there? There was 3. Okay? What are the 3? If you forget about this rule temporarily, what stable model do you get?
Bird, resident bird, and migratory bird.
So bird of Joe, resident bird of Joe, and migratory bird of Joe, right? Because when you forget about the third rule, nothing contradicts, right? Okay, so that's one thing. What about now forgetting about the fourth rule? What do you get? Migratory bird. But now you cannot derive that Joe is a resident bird because you forgot about the fourth rule, or ignore the fourth rule. And if you forget about this one for now, but then you get another thing. So, okay, and you will see that each of them will share the same probability. That's one of the slides that we had before. Okay, so these are the probabilistic stable models, but they do not correspond to the original program. because there is no stable model there. Okay? All right. So this condition is actually critical for the correctness of this statement. Are we together? Okay, good. Okay, so then we go to the next one. So MLN into LPMLN. Can you guess? How can we translate MLN to LPMLN? So again, suppose you don't have alchemy, but you have some system for computing LPMLN, which means you can use that system to compute MLN. How is it possible? Anything? Actually, you already know some hint here. We covered the similar thing before. Now forget about the probabilistic component of each of the language. Then LPMLN becomes like ASP, and MLN becomes like propositional logic or maybe first order logic, right? Do you recall the connection between ASP and the classical logic? No? There was some critical thing that we did. Yeah, okay. So lecture 11, go back to lecture 11. Page 14 has this slide. I hope you can still remember this. What happens is, do you remember this example? So P or Q. And P or Q has three models. So if you, so you want to compute these three models using ASP solver, right? Now you cannot do that by directly calling Klingo on this program, because then the stable models are only the minimal models. But I need actually the models that are not minimal, because PQ is a model there, right? So how can we use Klingo to generate these non-minimal models?
So we generate all possible solutions and constraints.
Yes, that's actually the idea there. And how do we generate all possible cases? Choice rule. So write choice rule, and then write this. Then you are done. Okay? That's what we covered a long time ago. Now I'm going to tell you actually some simplification of this method. You actually don't need to convert into the constraint. In the presence of choice rule, I can actually convert into this way. So all I need to do is to take the original formula F and add choice rule for all atoms. That's it. And if you call the Klingo on this program, you will get the models of the original program. Are we together? So you can easily use Klingo as a set solver, okay, or solver for computing propositional logic. I give you the formula in propositional logic. How do you use Klingo to compute? You just add choice rules. That's it. So the same thing actually happens here. So why do I have second example? Okay, let's just work on this. So what are the models of this? The first one, not Q implies P. What are the models?
P is model Q, P is model C. Q, P, and P.
How many interpretations are possible?
4.
4. Okay. And how many of them are true?
3.
3. Okay. So when P is true, this is true. When Q is only true, that's also true. PQ is true, that's also true. The only thing that cannot be is empty set. Empty set means Q is false and P is false. That means true implies false. So this is not the case. So there are 3 other 3 interpretations models. Okay? The exam is coming next week, so you better remind yourself. Okay, what are the stable models of this? And again, this is according to the theorem that I just talked before. You can actually call Klingo to do. You will see that there are also 3 stable models. Okay? So the idea is this: you are given some formula, okay, and you're translating this into another program where this translation adds choice formulas. Now what happens is when you look at the models of F are exactly the same as stable models of this translated program. In other words, we reduce the propositional logic into the language of ASP. Okay? Are we together? So, this is actually just a repeat of the theorem, except that I'm simplifying the constraint part, so you don't actually have to write even constraint. Okay, so basically, if you want to compute the models of propositional formula, just add choice formulas. That's it. And close, of course, Klingo. And so that's actually the case when we have no weight. How can we use this to embed MLN into LPMLN? So this is the statement. The translation is actually similar, except now you have to talk about the weight. And turns out that what weight that you assign is actually not important. Okay? So you just add choice rules. Same as before. Weight, what weight do we have to assign to the choice formulas? Just assign anything. Okay? Okay, so this is the theorem. Once you do that, by the way, here is a comment that effect of adding the choice rules is to exempt the atom from the minimization under stable model semantics. So the theorem here, any MLN and its LPMLN counterpart have the same probability distribution over all interpretations. Okay? So in other words, if suppose you have this MLN program, okay? How do you convert into LPMLN? Just copy the formula and then add choice rules. So you can write any weight, okay? It does not actually matter. That's it. Okay? All right, that's easy case. Now let's actually go to the hard case. So easy previous cases because they were coming from the way that the LPMLN was designed, because the LPMLN was trying to capture both of these languages. So that was actually the design goal, to embed each of these languages. But what's interesting is actually it's also a way to go back. So we are going to talk two things, LPMLN to MLN and LPMLN to ASP. And yeah, I hope I can cover two. Okay, so let's see. LPMLN to MLN. This process has a long history in knowledge view representation called completion. So what can be done here is to adapt that well-known techniques into this new setting of LPMLN. But the completion process is actually well known in the literature. So, so forget about the weight for now. Let's say what is counterpart here. Can we actually think about how to convert ASP into propositional logic? Let's only talk about this for now. Okay, what is your guess? How? So we learned all this ASP. Okay, now it looks like I'm telling some lies. Why do we bother with ASP if you can convert back into the propositional logic? Okay. All right. So this process is actually not very simple. Okay, so it takes some effort, and this is actually a typical problem that I give in the midterm, because this is easy to grade, okay, to see whether you are following the material. So this is a process that turns ASP program into propositional formula, okay. Again, the idea is the answer sets of the original program are exactly the models of F. So the process is now looks like this. You start with the pi, you translate into the professional logic. Now you look at the stable models of the program. They're exactly the models, okay, classical models of this translation. This is the goal. Okay, the reduction now is to reduce ASP into set or professional logic. Now this process that we are going to define works only for some fragment of ASP, although it can be extended to the general case. But for this class is concerned, we will only look at the special case known as tight program. Okay? So as I said, it can be generalized to turn any LPMLN program into MLN. But there is actually a problem with computation blow up, so we are not going to cover that in the class. Okay, so completion. What is the completion? So think about ASP program written in this form. So it has the form of A if body. So we are not looking at the general ASP program, but the head is a single atom A, and it appears only one time in the program. Okay, each atom appears exactly one time in the. I'm sorry, no, let's forget it. The atom can appear multiple times in different part of the program, but every head must be a single atom. Okay. In fact, we can also allow constraint. So okay, let me actually just ignore the constraint for now. Okay, we'll just assume this special case. So every head is a single atom, and body can be any formula. That's fine. So the completion is defined to be this one. So collect all the bodies that has A in the head, and write backward implication or reverse implication. So if you have body, for instance, so let's actually look at this one. So suppose there are two rules that has A in the head, okay? Then the completion is this formula. Starting with A, going reverse, and disjunction over all such bodies. So this is called completion formula, and the whole completion is the all such rules. Okay? So we'll do exercises in the next few slides. But the theorem is saying that for any tight stable answer set program, the stable models are exactly the models of the completion. I didn't define what is tight program yet, and I will ask you to figure it out in a moment. So let's actually look at the examples. We want to compute the answer set of this program. What are the answer sets, by the way? We just did it. Singleton set P and singleton set Q. That's what we know. Okay, this time we are not going to use the method that we learned before, but we are going to use the completion. Okay? So what completion does is copy the original rules. Okay, this is one part. But now there is a reverse arrow. So starting with P, for each atom P, you're going to write the implication that has P in the antecedent. So P implies something. The reason that P can be true is because there was a reason for P to be there, and the reason is not Q. So we write here. Same for Q. The reason for Q to be here is because of this rule, so this is it. You can actually understand this way. So suppose this is kind of cause, and this is effect. So not Q is there, it causes P to be there in the stable model, right? If P is there, then there's a cause for that, which is not Q. So this one is saying the other direction. If there is P is true, then not Q must have been true, because that's the only rule that can derive P. Okay? Are we together? So you need to know how to write these two additional formulas. But if you're done with that, that's already the end. Okay, that's the whole story. All right, so let's simplify this. If you have these first and third, how can you simplify? Or how can you combine this into one? Yeah, it's a double arrow, which is P is equivalent to not Q. Same way, not P implies Q and Q implies not P, so that's same as Q is equivalent to not P. But by the way, these two are actually equivalent. So the whole thing can be simplified into one formula. How many models are here? For P is if and only P is equivalent to not Q? Two. P satisfy this as well as Q satisfy this. And they happen to be the stable models of the original program. Are we together? It's a very simple algorithm, and maybe if you learned this method before, you could have saved some point in the midterm. Instead of computing the readout, you may have just did this way. Okay. All right. So let's do another exercise. P if not Q, Q if not R. What are the stable models? Do you know?
Q is 1.
Okay, we don't know yet. Okay, so let's check what are the stable models. So first, we copy the original program. Now, for each of the atom here, we have to write where this cause coming from, right? So for P, what was the cause? Not Q, so I have to write not Q here. For Q, what is the cause? Not R, so I have to write. For R, what is the cause? Nothing. Empty disjunction is bottom. Okay, that's it. So then, let's simplify this formula. I mean, the nice thing about this method is once you convert into propositional formula, you can use many techniques or many simplification methods that you know for propositional logic, right? So again, if you have these two formulas, how do you simplify? P is equivalent to not Q because there are different directions of arrows here. Same for this, Q if not R. And this one, how do you simplify? R implied bottom is same as? It's just not R, right? So R is false, not R, okay? Alright, so what are the models here? R, can it be true? No. If R is false, then Q must be? True. If Q is true, then P must be?
False.
So how many models are there? One. And what is that model? Q. This is the only one. And of course, you can check with respect to the readout way. Okay? Are we together? So here we talk about the models, which is this, which is same as the stable models for answer sets of the original program. Okay? Good. Alright, so then now the next question. So this method doesn't work all the time. I said it works only for tight programs. So what would go wrong if this condition is not met? Since I didn't actually say what is tight, you can actually imagine. Can you find some program that this method would not work? Well, I will give you just example then. What are the stable models of this program? P if Q, Q if P. What is the minimal belief that you can derive here? Empty set. Okay. All right. Okay. So what is the completion? So P if Q, Q if P. Okay. Now the completion is P implies Q, Q implies P. Okay. So this is same as just P is equivalent to Q. What are the models of this? Empty set is one model, but also PQ. Okay, so there is a mismatch. Okay, What is special about this program?
Completion is the same as
That's true, yes. Completion actually didn't give more than what we know for the formula, right? So we add something. Before, what happens was when we add completion, we actually give more constraint. So the models are not necessarily the stable models, right? So we can actually reduce the models that satisfy all these formulas. But this case, it is not. Actually, let's go deeper. Okay, so maybe there's also another example that it's not necessarily that completion does not add more things. It may add something, but it is not sufficient to guarantee the stable models. Okay. The basic idea here is there's some circular dependency. Okay. So what happens in the example is here, for P to be true, Q must be true. For Q to be true, then P should be true. And under the stable model semantics, of course, there is no reason to believe both P and Q because they are circularly dependent. But if you turn into the classical logic like this, there's no way to get around this problem. It's basically saying that P is equivalent to Q, P and Q are the same, but there is no such thing as minimizing those extent. Okay? So this idea actually does not work. It's because there is some circular dependency. Okay? So there's a notion of graph theoretic notion to define this class of programs called type programs. So let's actually imagine that we have programs of this form where there's a head and positive body and the negative body. Positive body means that there's no negation as failure. These are just positive atoms. And these are the negative literals. Okay? So negation followed by the atoms. Now we are going to draw an edge based on this program. First, if you're given the program like this, there are three atoms, P, Q, R. Each of the atom forms the node in the graph. And there's a edge from P to Q if there's a rule P if Q. So look at the rules. So for instance here, you can draw an edge from the head to the atoms in the positive body. Okay, so for this rule there will be M edges be drawn from A to A1, from A to A2, A to A3, up to A to AM. So for this example, you see this blue rule contribute to this blue edge. This red rule contribute to this red edge. Now this rule does not contribute to any edge because there is no positive atoms in the body. Okay, so the only dependency is between the head and the positive part of the body. Now once you have this, you will see that there is a loop, okay, that connects something. Okay, so here the formal definition of loop is a path of non-zero length, but basically you can easily identify from the graph. So there is a loop here, PQ. There's a self loop. Okay. So this program has cyclic dependency, so this is not a tight program. The program that has no cyclic dependency, there's no loops, they are called tight programs. Okay? So going back to the examples that we had, so this one, how many edges are there in the dependency graph? No, how many edges? There are two nodes, P, Q. The edges go from the head to the positive body. Positive. Only positive atoms in the body. So how many edges are here? Nothing. How many loops are there then? Nothing. Okay. So this program is called tight because there is no loop. What about this? How many nodes are there? 3. How many edges are there? Is the program tight? Yes. How many nodes are here?
2.
How many edges are here?
2.
How many loops are here?
1.
Okay, so this program is not tight. Good. Okay, so you're ready to take the quiz now. Okay, so I'm going to ask you to find all tight programs. Okay. Oops, C. Interesting. Okay, so this is actually choose all, so I cannot use. Let's see. Okay. Okay, good. Okay, so choose all tight programs. Okay, are we done? Okay, good. So, what is the solution? Okay, so some people said A, B, C, some people say C, D. Okay, D, D, D. Surprisingly, there are 4 people who said D and also C. Okay, good. So answer is actually A, B, C. So let's see why. I mean, obviously, first one, there's no edge, right? So this is tight. Second one, no edge, tight, right? So here, actually, this one is also easy because if you forget about the last rule, it's the same as what we just did. So there's a loop. So this is not tight. What about this? P, Q, R, S. So from P to Q, P to R. So from the first rule, you get 2 edges. The second one, Q to R, okay, and Q to S. And from the third one, you get nothing. But this one doesn't have any loops, although it has some edges. Okay, so there's no cyclic dependency, so this is also tight. So there are 3 tight programs, which means that the completion can be applied to these 3 programs to find the correct solution. It doesn't work for the last one, and what happens here is actually the completion is not actually strong enough. So there is actually more generalized version of completion that actually get the right stable models. What will happen is when the completion is not strong enough, you will get some models of completion which is not a stable model. Okay. All right. So this is what we did. Actually, now, so yeah, question.
Is there any use of non-type programs? Like why one should write this?
Oh, reachability. Transitive closure is a non-type program, right? So there's a lot of non-type program that is actually very, very useful. Okay. All right. So yeah, what I just said is it should be clear, right? When you have Hamiltonian cycle problem, it has cycle, right? So you cannot avoid that thing. Okay. many problems are actually cyclic. All right, so then how do we use this idea? So far we didn't talk about LPMLN or MLN, right? There's no weight. We are talking only about how to convert ASP to propositional logic. But now, having known this classical result, how do we translate? Well, assume that LPMLN program consists of this kind of tight program, okay? So you can have certain weight with some rules, A if body. Completion is actually the same as before, but what we assign for the completion formula is infinite weight alpha. And that's it. Easy, right? Okay, so I don't have example because it's so straightforward. Okay, so take any rules that you have before. I mean, if you want the example, I can just simply write. So this is LPMLN program. How do you convert into MLN program? We just have this one, and then write the completion formulas. And if you give to alchemy, it will compute stable models of LPMLN, original LPMLN program. Okay, and that's how actually the system was developed. So this is called LPMLN to MLN. Okay, so the architecture looks like this. You have LPMLN program as input. Of course, we have to assume this is tight, and the definition of tight is actually the same as before. The output of the system, it can compute marginal and conditional probability, or only return the most probable stable models. Now, of course, you can say that if you compute the probability, then looking at the probability, you can find the most probable stable model. But this computation is often saving the time. If you don't need to know the probability, but you only need to know what are the most probable stable model, then this can be much faster than computing the probability. Okay, because it uses optimization techniques rather than enumerating all the probabilistic information. Now inside the system, obviously there is a translator, LPMLN to MLN, compiler, that turns into MLN. And in this class we use alchemy as the main solver, but there are also other versions or other implementation of MLN called Tufi and Rocket. So this system can be used. And each of the system has different algorithms implemented. So some system actually works better for some benchmark problems. So there's no, that they actually are more or less compatible to each other. Okay. All right. Although actually some problems, those other systems actually work much faster. Okay. By the way, if you happen to know these systems, they actually have slightly different input languages. So what this system is doing is compile the MLN input into a few different ways. Okay, so the users don't need to know the subtle difference between the input language of these systems. Okay. Okay. Okay, so this is the example that you saw earlier. I don't have to repeat. Basically, the same thing that we did with LPMLN to ASP last class can be done with LPMLN to MLN, as long as if you work with tight programs. Okay. By the way, BaseNet is a tight program.
Yes. Yes.
In the BaseNet, by definition, the DAG is acyclic. So if we model the BaseNet using the MLN rules, this program is guaranteed to be tight. Okay, so that works well. All right, the next topic is actually LPMLN to ASP. I'm not going to go into the detail. I don't have time to do. So we'll come back to this later. But let me just mention to you one thing. In the case of LPMN to MLN, we know that this is limited to the type programs. For the non-type program, this method does not work. It's actually active research area where we can actually generalize this computation to non-type program using the method of alchemy. But there's some computational bottleneck, so that's a bit of problem for now. But it's actually another translation that we do into where we turn LPMLN into ASP. So then we actually don't have that issue. We can use ASP solver directly, which already handles the non-type program. Okay, so that's what we are going to cover next class. And I guess it's a good time to stop here. Any question about today's material? Okay. All right. So then let me open the Socrative.